Alrighty, P 16.6, this is the big one, okay? This is weak acids. Weak acids, because we know they're weak, we know that they partially dissociate. And because they partially dissociate, we have equilibrium. So this is definitely different from strong acids, okay? We got a lot of learning objectives here. So this is 8.2. You need to take a minute, maybe 2 minutes, and read, annotate. We have a couple new equations coming in from the equation sheet for the acids. And then when we get to video 16.7, I will show you the base part, okay? So take some time, annotate and read so you know what this new thing called is Ka and pKa. Weak acids, they only partially dissociate. So back in chapter 4, when we had a weak acid, it would hit water and it would dissociate into the H and the minus, but then you still had the whole acid intact. So here's the question. If a weak acid partially dissociates, so you have a mixture of ions and the acid, well, then the question is how much did the acid dissociate at all? So in chapter 4, we remembered because it's a weak acid, we're in equilibrium. Single arrows. Strong acids, weak acids were at equilibrium. Strong acids, single arrow. So we can just plug and chug, find pH, and call it a day. If the acid reacts with water, then you form hydronium. Remember, I don't always put the water in my equation, so then I would just say hydrogen instead. Either way, you're going to get your conjugate base as your other product, okay? Because remember, if this was the acid, it's going to turn into that conjugate base. When you don't put water into the equation, you can't really do that acid conjugate base pairing with it, okay? So that's why we put water in it if we need to. So a small percentage of the actual acid dissociates, ionizes, okay? So just a small percentage. The concentration of hydronium, actually what happens, it's way smaller than that initial concentration of that acid. So look at the diagram. I have a strong acid. Well, we know strong acids 100% dissociate. So whatever this concentration is, let's say it's 1 molarity, it's going to be 1 molarity and 1 molarity because that acid that is strong broke up into the H and the A minus, okay? But a weak acid only partially dissociates. So if this is 1 molarity, then what are these concentrations? Okay, so notice this is less than the initial concentration of the acid. And look at the H and the A minus, extremely small. But I'm comparing it to the acid. Okay, so how do we actually calculate this? Well, we got to do a little bit more math with it. But let's first start off with the particle diagram before we start plugging and chugging. So which of these two diagrams, diagram number 1, we'll call this number 1, or diagram number 2, which one's a strong acid and which one's a weak acid, and obviously explain. Well, I have my little key over here. So I see right here, I do have a hydronium, okay? And then I see 1, 2, 3, 4, 5, 6, 7. So these guys right here, okay, that looks like hydroxide, okay? So I have 7 of those and 1 hydronium. And then, or actually, I'm actually thinking it's not hydronium. I think that's actually, let me rewind. All right, this right here, because the little white one is H and this blue one, I bet this blue one is the actual acid. So we're going to call that the acid. So I have 7 of those. The reason why I think that, and I'm going to circle this in a different color, let's go orange, is because notice that one right there, there's no more little white one. So if I had to guess, that's the A minus, okay? So remember, if this is a strong acid or weak acid, that acid dissociates, you get that conjugate base. So I have one hydronium and one of that, and I still have 7 acids. Okay, well let's check on the other side. Over here I have hydronium. I have 1, 2, 3, 4, 5, 6, 7, 8. So I got 8 of those. And then I have this individual atom, which remember we said was the A minus. And 1, 2, 3, 4, 5, 6, 7, 8. I got 8 of those. Well, this right here, this is a strong acid. And why? Because I have the same concentration, same amount, hydronium, and the A minus. Remember my equation at the top for a strong acid? H, and I'm going to have to put the water in here because I drew hydronium. Liquid, single arrow because it's a strong acid. I'm going to get my hydronium, and I'm going to get my hydroxide. Okay? Sorry, not hydroxide. I'm going to get my conjugate. I was doing a little double replacement there. My conjugate. But because both of these, it's a 1-to-1 ratio, you have the same amount. Okay? And notice also in here, there's no more acid. There's no more acid. It's gone. Because the acid is this little single hydrogen with this bigger blue atom. So there's not even acid in here. So this one right here, that's my strong acid. Why is this one my weak acid? All right. Well, as you see right here, I have 7HA. And the majority of this weak acid didn't dissociate. And how do I know? Because I have one hydronium and I have one conjugate. We don't ever draw water in the picture because it's just way too much to put in the box. But I do have these two 1-to-1, but I still have way more acid than I have of hydronium. But the hydronium is going to be equal to that conjugate. I have way, 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 way more. I have 7 of these versus 1 of each of those. So that's how I know the weak acid is still intact. Okay? So if you don't have a particle diagram, what else can you use? Well, we have what's called Ka expressions. Okay? Obviously, K stands for equilibrium. Okay? So there's the K. And then the A is the acid. So Ka expression, and I'm going to write this big, only for weak acids. Okay? You only have Ka expressions for weak acids. Notice we didn't talk about this in the last video, strong acid. So the Ka is called the acid dissociation constant. So how much does it actually dissociate? Sometimes it's recorded as pKa, and you do get this equation on the equation sheet. So if the pKa is the negative log of Ka, you could even go the other way, like the antilog, 10 to the negative pKa. So if you're given pKa, then you can solve for Ka. That value of Ka, it tells us a lot, okay? So this is what happens in your equation. There you go. Now I knew that was the acid. The acid, and remember this is a weak acid because I see that right there, equilibrium. And we would not be talking about that if it was strong. I'm going to get my acid, my water is going to be my base, and my hydronium is going to turn in my conjugate acid and then conjugate base. We write an equilibrium expression, and remember we write products over the reactants. But who do we not care about? Well, we don't care about water. And why? Because water is a liquid. That's why when I do my equations, I don't put water in my balanced equations because I don't want to focus on the water. So I do have my products over the reactants, and because only aqueous, which that's all we've been dealing with, and gases. Don't think you're going to see any gases in this chapter, okay? So products of the reactants, Remember, the water and hydrogen, they're interchangeable. Okay. Now, what does this Ka value tell us? Well, first, number one, strong acids, there is no Ka values. No Ka values. And why? Why? What do we know about strong acids? It's because they completely dissociate. What that Ka value tells me is how much the acid dissociates. You're going to notice that these Ka values are going to be like a number times 10 to the negative something. It's that negative exponent. If that negative exponent is like -1 or 2 or 3, that means that the weak acid dissociated a lot more than we thought. So the weak acid dissociated more, okay, than a normal weak acid would. But if you have that exponent that's like -5 and -10 and -12, okay, if that exponent is what it is, then that means that weak acid hit water, and it wasn't scared of water, okay? Water is actually scared of that acid, okay? So that weak acid hardly, barely dissociated. So we have a calculation for that. So the larger the Ka, but be very careful, these Ka values have these negative exponents. The stronger, I should put right here, the stronger the weak acid is. Remember, it's only about weaks. If you actually had pKa, you would notice that these would be very low values. So very low values also for pKa is the stronger the acid. pKa is related to pH. Okay? So if you have very low pHs, that means you're very acidic. Okay? Higher pKa's, that means it's not as acidic. It's a weak acid. Okay? So the larger the Ka, if I have my exponents, -1, 2, 3, even 4, stronger the acid. Okay? The smaller the pKa, the stronger the acid. Okay? So what if AP gave you this equation? Calculate, or notice the relationship. I have this acid, which this is acetic acid, Mr. Vinegar, hits water and breaks up into my ions, and there's my Ka value. But then I have hydrofluoric acid, reacts with water, and I get a hydronium, and I get the conjugate base. And I have this Ka value. The two examples of the weak mono means one hydrogen, okay? Diprotic means it would have two hydrogens, okay? So of acetic acid and hydrofluoric acid, their equilibrium dissociation Ka's are above. Which of the two acids is stronger and why? All you have to do is look at the exponent. Which exponent is larger, is greater? Remember, these are negative exponents. -4 is greater than -5. So this HF, and I would be telling AP this, HF is a stronger acid, and you always have to mention the other one, then CH3COOH, due to what? What's your evidence? Due to HF having a greater Ka value. And that's it. If they would have given you pKa, then you would talk about pKa. Okay, just get to the point. So, unfortunately, with weak acids, ice is back. Okay? Ice is back in a big way anytime you have a weak substance. So, rules for calculating Ka if you have pHs. Okay? In order to find the Ka, which looks like we're going to do a sample example right now, we need to know all the equilibrium values. So for all the equilibrium, that's how we're going to find Ka. The pH, here's the cool part. The pH tells us the H plus at equilibrium. To find Ka, we use the pH to find the equilibrium of H plus, And then we use stoichiometry because it's going to be a one-to-one relationship, those products. Then I can figure out all the other equilibrium. We put it in, we substitute, we solve for Ka. Okay? All right, so I'm going to be solving, and we'll make some notes to the side. So if I have this acid, formic acid, and I have this pH, and at that temperature, I want to know the Ka value. Well, first of all, I need to recognize this acid is a weak acid. And if it's a weak acid, that means I need to do ice. Okay? Every single time weak acids do ice. So number one, we need a balanced equation. Okay? So because it's a weak acid, whether you want to put water into the equation, that's your choice. I don't. So I'm just going to go straight here. But I'm going to put right here in a different color. If you do put plus water, you will get a different product instead of hydrogen. So instead of H plus, you would get hydronium instead. Either one is fine, ladies and gentlemen. You know my thing. Okay. Number two, set up your ice. Okay. So initially, my concentration of the acid was 0.10 molarity. Initially, I don't have any products. And why? Because think of it, at time 0, you only have reactants. You don't have products. And what do we know over time? Well, my reactants are going to start to disappear. And because I don't have anything else to go off of, my change, I'm going to use an X. Okay? My reactants disappear over time. So my X is going to be negative X. And because my products appear over time, I'm going to use positive X. Okay? Now, why is it negative X and then X and X? Remember, everything is a one-to-one ratio. You're going to like this part because you're not going to see any coefficients. Okay? So my equilibrium is 0.10 minus X, and then 0 plus X, and then X and X. Okay? So, once I do that, now number 3, you need your Ka expression. So my Ka expression, always got to write a K expression, products, so H plus, concentration CHO2, don't forget your charges, and then the acid. Okay? Now plug in your values. So I have X and X. The same thing as saying X squared over 0.10 minus X. Okay? You don't have to say X times X. You can say X squared. And we're trying to find Ka. Okay? I don't know Ka, but what happens when it looks like I need to use like a quadratic equation? Okay? So, you can make an assumption. Okay, so remember there was another piece of information that they gave us. They gave us pH, okay? And what did we say above? pH gives us the equilibrium concentration of H+. So this pH right here, I can solve for these two, okay? Because remember it's going to give me H+, and then using stoichiometry, I can get that value. So I'm going to put right here using pH. Okay, so pH is 2.38, and to get the hydrogen concentration, I take 10 to the negative 2.38. Okay, so let's plug that in. Second function log negative 2.38, and I'm going to get for my H plus 0.00417, and that's molarity. But who else is that concentration? Well, that concentration is also the other product. It's also CHO2 negative because of the 1-to-1 ratio. And then now I have the numerator. I have Ka, this X, 0.00417, and I'm going to square it. Okay? Now the denominator, 0.10 minus that 0.00417. Because this value is so small that when you take 0.10 minus this value, it's going to probably be 0.10 in the end because of sig figs. Okay, so plug it in. So at the very top, you do have a square button. So 0.00417, and then we're going to square it with 3 sig figs. You get 1.74 times 10 to the negative 5. Down at the bottom, 0.10 minus 0.00417. And like I said, with 2 sig figs, because of the calculator says this, 0.095, but because of sig figs, I need 2 after the decimal. This 5 is going to round it up. And look right there, practically nothing. So I'm going to take that 1.74 E button, negative 5, divide by 0.10, and my Ka value was 1.74 times 10 to the 4. Now, K values, just like Kc and Kp, Ka values have no units. Okay, no units, no units. So, after I did my Ka expression, we're going to use an X. Okay, use, step number 5, use pH to get to that H concentration. Okay, and then plug in, solve for Ka. Now this Ka, that exponent, okay, that's not bad. That acid probably dissociated a little, but how can we actually get a number of how much to dissociate? Well, part B, there's a calculation. It's called percent of ionization. Okay, so here's the rules. Okay. Percent of ionization, before I get to this part, the higher the percentage, the stronger the acid. So what you do is you have this equation. Now notice it's not in pink, so you got to know this equation. You take the H of equilibrium, which most of the time it's our X, divide by the initial acid times 100. So let's do that up here. So our X, here's part B. So we write first the equation. So percent ionization, and you can abbreviate it, the H plus at equilibrium, okay, over the initial acid. Well, make sure you write the actual acid formula, and then we put little I. Well, H at equilibrium, this equilibrium is the X's, okay, because remember, we just solved for X. So I'm going to take that X 0.00417 molarity over the initial acid 0.10 molarity. Now, these molarities are going to cancel, but the other thing that I didn't write is, remember, this is percent. So we're going to go times 100. So divide times 100, or move the decimal 2 places. We don't use that 100 for sig figs. So with 2 sig figs, 4.2%. Now what does this mean? So this acid that hit water dissociated 4.2% into that H plus and CHO minus. That means 95.8% of the acid did not dissociate. I like to think of it like a little cookie. 5%, okay? Probably like a big crumb of the cookie dissociated. The rest of the cookie, aka the acid, is still intact, okay? So that's pretty much what it is. So percent ionization, this is how much the acid dissociated, okay? So how much the acid dissociated, okay? All right. Sometimes maybe we don't have pH, so we have to do something else, okay? So what if we actually want pH and we're given concentration, okay? Well, the other thing that you need to know too, and I didn't put it on here and I'm just noticing, I need to also give you the Ka value. So notice in the directions up here, what if we, in order to find Ka, we had pH? So in this case, we actually know pH. We're going to find Ka. Well, in the other scenario, what if we actually know Ka, which I'm going to give you the value, and we have to solve for pH, okay? All right, so let me find that value. So I have the concentration of this acid, and what is my Ka value? Okay, I found it. Excuse me. 4.9 times 10 to the 10. Look at that exponent right there. When I do this calculation, that means that this acid barely dissociated. He hit water and he scared water. That's pretty much what it is. So remember our rules. Number one, write your equation. HCN, now remember this is a weak acid. Equilibrium, H plus and Cm minus. Now, there's some notes up here I haven't talked about yet, but I'm getting ready to do it. But let me start this first. Now we do our ice chart. My initial concentration's 0.20. I don't have any products. I have literally nothing else to go off of, but I need to solve for pH. So I'm going to do my change, my negative x, x and x, and then my equilibrium, 0.2 minus x, x and x. Number 3, write my Ka expression, so my products, over my reactants. Remember, don't include water. Now, this time, I actually know my Ka value, 4.9 times 10 to the 10. But I don't know anything else. So I can't use pH to solve for x. So now I'm going to have x squared, x times x, over 0.2 minus x. What this is looking like is something called the quadratic equation. So, in a different color, with what you see right here in orange, you would have to use the quadratic equation. And some of you are like, oh my God, that was IM0. I don't want to be doing that. But we have a little trick in chemistry, okay? Because it's not that we're lazy. It's just called efficient. Let me show you something, okay? What do we do if we're faced with having to solve a quadratic equation in order to determine x? Often this can't be avoided. So if the Ka is so small, and remember, look at the exponent on Ka. That anything basically above -5 and on, so small. So small, it's basically negligible. We can make an assumption. We can assume something. We can assume that x is so small compared to the acid that x, when I subtract, isn't going to matter. So what I mean by that, when I take my initial concentration minus x, I'm still going to get my initial concentration. So small. Okay? Now, the problem is, by us assuming, we have to check. And how do we check? We use percent ionization. Okay, so let me show you first, then I'll come back to this. So we make a note instead. I'm not doing the quadratic. We say assume, and we put it right next to this. We assume that x is so unbelievably small, and why? Because look at that exponent, -10. That this x right there, when I subtract it, it's not going to mean anything. I'm going to get the same thing in the end. Okay? So what you're doing is you're getting rid of that x. Don't erase it. Just do a little cross out, and that's it. So then I have 4.9 times 10 to the 10 equals x squared over 0.2. I just avoided using the quadratic equation. So now here comes basic algebra math. We're going to bring this guy up, and we're going to multiply, and then we're going to take the square root. So I'm going to show you step by step. Eventually, you won't have to show me all these steps. 4.9 e button -10 times 0.2. I'm just showing you step by step right now. You're going to get 9.8 times 10 to the -11, and then I have x squared. We're going to take the square root of both sides, so that way I can just get x. So square root of that 9.8, and I'm going to get 2 sig figs, 9.9 times 10 to the -6. Now, who is this x? This x is molarity, this is H plus, and it's the other product. And why? Because they were both a 1-to-1 ratio. But how do I know this assumption is valid? Okay, so now here comes the new steps. Okay, so if you have to assume, okay, you have to check your assumption. Okay, and by checking your assumption, because you can't do anything more until you check it, you have to use percent ionization equation. Okay, so I'm going to check it. I apologize, I'll give you more space. I'm going to show them that percent ionization. I'm going to say the word check. I'm going to check it. Percent ionization is my H plus at equilibrium, which remember this x is at equilibrium. So 9.9 times 10 to the 6 molarity. And I'm going to divide it by the initial acid. So this acid was HCnI, which was 20. But don't forget, times 100. Times 100. So we're going to take that 9.9 to the 6, divide by 0.2 times 100. Okay, very small number. So this percentage, sorry, I'm out of room. I don't like to cut it off right here. I'm going to get 0.0049%. People, that's barely a crumb. Barely a crumb. So, how do you know if this is a good assumption? So here's the rule. Okay. Check to see how large it is compared to the initial value. So we use our percent ionization. If the x, okay, remember this x was the assumption. If the assumption is less than 5%, it's a great assumption. So no need to use quadratic equation. However, if that x, it just has to be above 5.0. If it's above 5, it's a bad assumption, and then you got to go back and use the quadratic equation. Okay, so the assumption, not valid. But do you see the next line of notes? AP realized that using the quadratic equation took so much time. So the point is, the assumption will work on the AP test. If by chance you're solving one of our problems in class and it's above 5%, you would just say assumption not valid. But we're not using the quadratic equation regardless. Okay? So this, not on the AP test. Yay, 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 yay. Okay? So in the notes right here, I just showed you exactly what we did. So using the Ka, Okay, we can calculate H plus using our balance equation, show equilibrium. Look at the value of Ka, but I gave you the value. Okay, but there is a table that we're going to use. Okay, write down the initial and equilibrium values, not water. We're going to use our assumption for X, and then we're going to plug it in the quadratic, and then we can solve pH. Okay, if the assumption worked, which ours did, then we can solve for pH. If the assumption didn't work, we can't solve for pH, okay, because we'd have to use the quadratic equation. So now that we know, and I'm going to put over here, I apologize, pH is the negative log of H plus. Well, I have my H plus, it's right there. So there's my H plus concentration. So pH is the negative log of that 9.9 to the negative 6. And remember that exponent tells me the answer is going to be close to 6. So negative log of 9.9 E button negative 6. And 2 sig figs, 5.0. There's my pH. Now remember, what did I start with? I started with a weak acid. My pH better be less than 7 because it's an acid, okay? And it was a weak acid, so it wasn't a low acid, okay? Polyprotic acids, last topic of this, okay? Polyprotic acid means that it has more than one proton, okay? So remember, we called it monoprotic in that practice problem number 1. Monoprotic just means one hydrogen in the acid. Polyprotic just means either maybe you have 2 hydrogens or you have 3 hydrogens. Just means you have more than one proton. So the problem is the protons, they're removed, but you can only take one at a time. So take this acid, and I don't want you to think this is a strong acid. This is sulfurous acid. Sulfuric acid is a strong acid, okay? So sulfurous acid, if I have H2SO3, I took one hydrogen, because this is the key part. You can only take a proton one at a time. I'm still going to be left with a hydrogen, but notice my Ka value, 1.7 to the negative 2, okay? That's going to dissociate pretty good, okay, without doing the math. Then I take that product, I react it with water, okay, and I do it again. I take the second proton, dissociates, and then I'm left with the polyatomic, no more hydrogens. So there is no Ka3 because I'm out of hydrogens. So notice that Ka2 got smaller. So that means that HSO3 dissociated even less than the original acid. Okay? That original acid did the most dissociation. So that Ka1 is the dissociation for the very first proton released. And the second one is for the second one. But this is the key part. It is way easier for us to remove that very first proton than the second one, then the third one. So if I actually had a Ka3, I just know that exponent is going to be probably, I'm just making a guess here, maybe negative 12, 13, negative 14, 15. I just know it's going to get even smaller and smaller and smaller. So therefore, the Ka, the majority of the acid that dissociates, it's that very first Ka value. Okay? So right there, the very first one. So the majority of the H concentration at equilibrium usually comes from that very first ionization. Okay? I'm going to show you the Ka chart when we do sample problems from the book. But before we get to the second part of the beast, I'll see you on the next one.